Actually, my topic today actually goes back to Jean-Marc's very early work. If I remember, he did his PhD in Australia, if I remember correctly, with Ernie Tuck, yes. And I think, I don't know if this was his PhD topic but it was close when they worried about the free surface response of a flow past a submerged body. And they had noticed, or it was known from earlier work, that this is there is a very interesting situation there in the limit of so-called low fruit number. So the body is, the flow is slow, let's say. The interesting thing is that if you try to compute the flow, the free surface response, in powers of the fruit number, then you never get a result that is 0 to all orders. This was a very peculiar behavior that I think Ernie Tuck was interested in that, and I think probably Jean-Marc also got interested in that through Ernie, and they have an important paper in either Proceedings of Royal Society or Transactions, I can't remember now, where they apply summation techniques for series to try to capture the free surface response. Now it is known that the free surface response is exponentially small. It's non-zero, but it's exponentially small with respect to the fruit number. That's why you cannot capture it in a power series. And the field has advanced significantly, and I'm going to talk about some recent work we did in this area. Okay, so I think it's a very fitting topic for Jean-Marc's approximate birthday, right? Tell us where the approximation was, above or below. I think I know the
Some things I don't say.
Okay, so so this is a little bit of an outline. We're going to talk a little bit about motivation. I already told you some motivation, but this is a more specific motivation in terms of a model problem, and then the application to water waves, and go show you some results and some related problems we're working on. Okay, so here's the motivation. Motivation is this innocent looking ordinary differential equation you can see here, ordinary differential equation with forcing here. Now, you may think of this as the steady version of the Kordovich-de Vries equation if you assume steady response. So you're in the appropriate frame where the response is steady, and therefore you apply a radiation condition, as you have to do in this case, where the response is, you say, 0 far downstream, make the solution unique, and you wish to compute the response in the limit of weak amplitude here, so epsilon is small, but also in the limit where this dispersive term is small as well. So this mu here parameter, which as you're going to see is analogous to the fruit number in the water wave problem, measures wave effect, and this measures nonlinear effect. This problem is very easy to convince yourself that if you do find the solution in powers of epsilon and mu squared, you're never going to find anything in the far field. That is, if this is locally confined, the forcing, you're never going to find any waves because the expansion in this case is kind of trivial. And it's easy to see that you're not going to find any waves. Yet, if you solve this problem without the nonlinear term by Fourier transform, then there is waves which come from balancing these terms, and the waves because mu is very small, the response is associated with very large wave numbers of the forcing. So if the forcing drops off exponentially for large wave numbers, then the amplitude of the response is going to be exponentially small. So we would, this suggests looking at this problem, but accounting for nonlinear effects. Then you may say, well, that's probably not a very interesting problem because the waves are of exponentially small amplitude, and therefore, okay, the nonlinear effects are going to be really, really negligible. That's not the case. That's actually the absolute, it's the opposite. That even though these waves are exponentially small, they're controlled by nonlinearity as much as they're controlled by the wave effects. And in general, you have to do nonlinear exponential asymptotics. So in a nutshell, that's the whole message here, and I would like to explain. In this model problem, because of the linear solution through Fourier transform, this motivates working in the wave number domain, that is reformulating the problem in this form where the nonlinear term translates to this convolution integral. And here is the Fourier transform of the forcing. And here you can see, of course, the crucial part, which is which gives you the poles in the wave number domain, which give you the response. Now, if you assume, we're going to assume that the forcing is smooth, so enough, so it has exponentially decaying behavior, as you can see for large K, and also has a power in front of it with a power here alpha. That plays a role, as you're going to see. Now, this kind of forcing includes many possible forcings, this asymptotic behavior. But if the forcing has kinks like half a cylinder and so on, then it doesn't include it, because in that case, the Fourier transform drops off algebraically. Anyway, the message here, of course, is the residues here determine the far-field wave response. And the question is, if you find the residue, then you're done. But the thing is, the residue depends on this nonlinear term, even though this multiplied with epsilon in an order one way. This is interesting. And what is even more interesting is that depending on this power alpha, only if alpha is bigger than -1, computing these residues requires exponential asymptotics. How do you know these things? I'm not going to talk about them in detail. How do you know these things? Well, the thing is that unlike this equation in the physical domain, that if you expand in powers of epsilon and mu squared here, you will never see waves. So everything goes smoothly, no sign of waves, and no sign of non-uniform behavior either. In this case, if you expand in powers of mu square and epsilon, you start seeing non-uniformities. That is, this expansion becomes non-uniform for large K. So this is always, somebody does perturbation theory, that's always a sign that something is going on. And furthermore, depending on how epsilon relates to this mu square, this non-uniformity due to nonlinearity can become as important as this non-uniformity, which of course is to be expected because of the residue. So this is a very interesting, very rich problem, even though the equation looks innocent. Very simple differential equation. The behavior is very rich as far as the wave response is concerned. Okay, so how do you handle this? Well, this is actually in the wave number domain. You can apply techniques of multiple scale asymptotics, which you cannot do in the physical domain, really. So in the wave number domain, you have a rescale wave number kappa, which is mu k in this order 1. This to be expected because the residue corresponds to the linear residue kappa equals 1. And then the response for the Fourier transform, you can write it in this form. So it has the exponential. This is a fast exponential which is also the linear theory has. But there is a slowly varying amplitude here that depends on kappa, and you rescale also in this way. So this is the proper expansion in the large wave number range. And the proper scaling of epsilon and mu in order for nonlinearity to come at the same level as wave effects is actually this. This requires some analysis, which I'm not going to show you. This ultimately leads to a nonlinear integral equation for u of kappa, nonlinear integral, and the residues at kappa plus or minus 1, you have to solve this nonlinear integral equation. So it's a fully nonlinear problem, even though the waves are exponentially small. Okay, so what do you find? This is a summary. The wave response is sinusoidal, it has an amplitude r here. The wave number is 1 over mu, is very short wavelength, and there's a phase theta. This is in the downstream region. Upstream, there are no waves. So the response depends on this alpha, which is the power at which the Fourier transform of the forcing drops off. And you can see here the amplitude. What is in black here is the same as the linear response. So for epsilon equals 0, this parameter c is 1/2. This is the linear response. But from this nonlinear integral equation, when alpha is positive, they see some other number, which is bigger than 1 or less than 1. So you change the amplitude by order 1. More interestingly, when alpha is equal to 0, the amplitude is modified in a more crucial way. There's some factors here, like the gamma function and so on. Most importantly is that the power in mu, which is alpha plus 1, when alpha is equal to 0, linear theory says it's 1 over mu. Well, the amplitude of the forcing comes here. So this controls, and the phase also is modified. So when the amplitude of the forcing, when the forcing is positive, is a bump, let's say, the response is bigger because the A here is the denominator. When the forcing is like a hollow thing, like a valley, this A is negative, so the response becomes smaller, so the magnitude changes. And even more interestingly, when alpha is between 0 and minus 1, the nonlinearity modifies even the exponent. This is quite complicated, so I'm not going to talk about it today. When alpha is less than minus 1, nonlinearity is important, but you don't need the exponential asymptotics. Where is the exponential asymptotics? The exponential asymptotics is in this nonlinear integral equation, which basically sums up all the contributions that are encapsulated in this amplitude. So it has a lot of depth, this very rich behavior. Okay, so this is the motivation. Now, if you go to free surface waves, I'll show you about past bottom topography. This is the usual geometry where you have a uniform stream, encounters topography, and you have waves downstream. The star variables have all dimensions, and this is the characteristic length scale for the waves, the u square over g. And you have parameters. You have a nonlinearity parameter, which is the ratio of the amplitude of the topography divided by this length scale. You have the Froude number, which is like mu in our previous example. So it's f squared, and that's basically the ratio of u squared over g divided by the length scale of the forcing here. And there's also a depth parameter, which I'm going to assume that the depth is comparable to this short length scale. This is not a necessary assumption. Just to be specific, you can assume the depth to be larger than that, but this just to focus for this short talk. So you have weakly nonlinear, low Froude number. These are essential, and shallow, but not shallow. Still, dispersion is there. Shallow because the depth is comparable to u squared over g. Okay, So the thing is that this problem can be handled in exactly the same way as this force KdV I showed you earlier. And this is the forcing and assume the topography to have behavior like we assumed before, with the power alpha here and the exponential for large K. The response over the very surface is written in the same way as a slowly varying amplitude here in the wave number domain, of course, a fast exponential, and this is the scaling of the nonlinearity with the wave effect, same as before. And the wave response, again, takes the same form as before. This kappa naught is actually the actual wave number scaled that comes from the usual steady wave dispersion relation. And for alpha positive, it looks like the linear response, but with a different amplitude here. For alpha equals 0, again, you modify the magnitude in a serious way, depending on whether this is a hill or a valley. You expect big results, big differences. And also there's a more complicated case I'm not going to talk about, where alpha is less than 0. Okay, so I want to spend some time showing results. The results are amusing. This I'm showing for this kind of a forcing, which corresponds to alpha equals 0. Okay, so this has the required behavior, the Fourier transform. In the Fourier domain is a nice smooth obstacle where B naught positive is a hill, B naught negative is a valley, and alpha is equal to 0. So we expect pretty dramatic nonlinear effects here. The fruit number, notice, is only 0.45. This is a theory which is valid nominally, strictly speaking, for very small fruit number, but that's 0.45, and the depth parameter is 2. Okay, so this is for this amplitude of the forcing 0.04 and this 0.08, and I'm showing the numerical results are the exact solution numerically obtained from the water wave problem. The dotted is the dashed is the linear theory, and the exponential asymptotics is the red one. And if you see for positive forcing, linear theory is pretty small, as you can see. Nonlinear and exponential asymptotics agree quite well. There's a bit of a phase shift. When you increase the amplitude of the forcing, linear theory almost way down here. Nonlinear, you see much, much bigger. You see big differences. And the opposite happens when we are having a valley, that is B naught is negative, minus 0.04 and minus 0.08. You see the linear theory is now the dash is much bigger than the actual response, and which is numerical, and the exponential asymptotics. And the result, of course, is quite even more pronounced as the amplitude of the forcing increases. More interestingly, here this shows the wave amplitude versus the topography amplitude, again for fruit number 0.45 and depth parameter 2. This is the magnitude of the response, the amplitude, as a function of the amplitude of the force in 0, here positive, negative. So hills here, valleys here. And you can see the linear response in this scale is down here. It's almost 0 in this scale. And you can see for positive B naught, the response is huge relative to the linear. And the theory is capturing the exponential asymptotic, is capturing this very nicely. For negative forcing is practically 0. It's smaller than the linear theory, but anyway, it's practically 0. This shows you the ratio of the nonlinear to linear amplitude versus the topography amplitude. And the first plot here is for fruit number 0.45. So it's the ratio of the actual amplitude to the linear amplitude. By the way, the linear amplitude, of course, in the linear theory, whether it's a hill or a valley, you can scale it out, and one is the negative of the other, needless to say, okay? So you see the ratio for positive forcing for this fruit number, I mean, shoots up to 80 here. And even when the amplitude is 0.1, so yeah, the theory, the exponential asymptotics is doing a pretty nice job. And it's, of course, minute for negative forcing. For fruit number 0.71, even though, remember, this theory is for small fruit number, and the same depth parameter, the same overall feeling. The result is not as huge, but still quite significant, because, of course, the magnification, nonlinear magnification or depression is more dramatic relatively as the fruit number becomes smaller. But the actual amplitudes, of course, are smaller as the fruit number becomes smaller. So this is a situation of really, you cannot call fruit number 0.71 a small fruit number. And yet, as you can see, the theory is doing very well. And of course, linear theory, essentially, except close to zero, where the ratio is 1, is not doing well at all. I mean, it's has very, very limited ability. So I want to now talk about some extensions. The first two here are pretty straightforward. One is, as I said, the depth parameter, the depth being shallow, that is comparable to u squared over g, is not a real restriction. You can do the expansion. You need a little bit of modification here in the exponential by a little parameter here, which gives you this ratio. But the theory still goes through, and you can have the response depends on this parameter c for alpha n alpha equals 0. So the theory is a little bit different, but more or less the same result. Also, it's not surprising that you can do similar things if the forcing comes from a pressure which moves on the free surface. Same thing. The pressure as of this form, it depends on length scale L, normalized with rho u squared. The pressure Fourier transform, if you take it to be in this form, plays the role of the topography, and it's pretty much the same. The analysis is very similar, low past topography. So these extensions are pretty straightforward. What is much more ambitious, and we have made some progress here, this is the case of a two-dimensional wave pattern. So this is more along the lines of what Ernie Tuck and others were interested in, Francis Ogilvy and all these ocean engineering people. These are the Kelvin wakes and how they're affected by low fruit number when the pod is submerged. Now, this equation here, which I have written, I claim that this 2D model equation is a very convenient equation for developing a theory, exponential asymptotics in two spatial dimensions. That has not been done before, as far as I know, because among other things, that you cannot use complex variables for the two-dimensional problem. So it is much more difficult. So if you look at this equation, this has some very nice features. First of all, if you ignore the y dependence in the second spatial dimension, and here in the forcing as well, this is precisely, if you knock out one derivative with respect to x, this is the force KdV we were doing before. So this equation may be viewed as a two-dimensional extension of the force KdV. More importantly so, however, if you look at the wave part, so this has, of course, a quadratic nonlinearity, but the wave part here, the dispersion relation of this agrees with the deep water dispersion relation of steady waves. So the linear aspects of this problem coincide or mimic the linear aspects of deep water waves, steady deep water waves. So you expect Kelvin wakes and so on. So this is a useful equation for developing a theory, a nonlinear theory for nonlinear Kelvin wakes for low Froude numbers, okay? And indeed, with my collaborator, Takeshi Katoka, who is on the faculty at Kobe University, we looked at this equation and we developed a two-dimensional exponential asymptotics for this one. So the linear wave response mimics the classical Kelvin wake, and the amplitudes are exponentially small with respect to mu, which plays the role of the Froude number in the fluid mechanics problem. As the Froude number becomes small, nonlinearity cannot be neglected for small but fixed epsilon. This is non-uniform behavior that actually was noted way back by guy who worked with Tuvia, Milo, Gideon Dagan. He noticed that this very smart person way back. This is the important thing: as the Froude number goes to zero, you cannot neglect nonlinearity for small but fixed epsilon. It's a very non-uniform behavior. We find similar results to the force KdV. Nonlinear effects or wave amplitudes for the Kelvin wake are quite significant, and we submitted that for publication. We don't have acceptance yet. And we're now working on adapting this theory to the gravity wave pattern due to submerged sources like a submerged source or a doublet, and in the low Froude number, and we don't have results yet. So this is a significant, if it is successful, we feel this is a significant step forward. Okay, so, I'm okay with time? Yeah. All right, yeah. Very good. Okay, so let me then take the last few minutes to summarize and conclude. We use the force KdV as our motivation for studying steady gravity waves by flow path topography and other forcings in the weakly nonlinear low Froude number regime. A very interesting aspect of this problem is that even though the wave amplitudes are exponentially small, as the Froude number goes to zero, nonlinearity cannot be neglected for small but fixed epsilon. And you actually need exponential asymptotics in this limit, and you have to consider a joint limit epsilon and f becoming small. So it's a very delicate regime. The results are quite stunning in terms of nonlinearity, because the nonlinear effects, they differ fundamentally depending on the topography profile, that is that parameter alpha, for example, and whether the topography is a bump or a trough, and the water depth also come in, and the response can have very interesting departures from linear theory. The theoretical predictions have very wide validity, range of validity, even for moderate Froude numbers like 0.7. In contrast to linear theory, which is limited to really very small force in amplitudes. You can easily generalize to finite depth and to a moving surface pressure. This is straightforward. And in more recent work, we developed an exponential asymptotic theory in two spatial dimensions for a model equation which mimics the Kelvin wake of submerged sources in the low fruit number. And our current work has to do with trying to adapt this theory to the actual water wave problem to understand what happens in the low fruit number regime. Okay, so thank you.